A warm welcome to everybody. It's 12 o'clock, just after. This is part 2 of our ongoing webinar series on heat pumps. It's brought to you by the Northwest Net Zero Hub. This is done in collaboration with Stiebel Eltron, and they, as per our last webinar, will be delivering today's technical presentation. If you've missed any of our earlier sessions, don't worry, they've all been recorded. This one will be, and we will share the links to you after the session, so you can find them on our website. My name is John Mullins. I'm the Estate Decarbonisation Lead here at the Northwest Net Zero Hub, and I'm joined by Namitha, who is been doing all the lion's share of the work in the background to make this happen, along with Matt. A quick note about the hub for those of you joining for the first time: we are DESNZ funded. We're part of a regional network of hubs across the country, and our role is to provide free support to public sector organisations on their decarbonisation journey, whether that's strategy, planning, implementation. We're hosted here by the Liverpool City Combined Regional Authority, and that's why you may have seen event emails coming from Mersey Travel or similar. They very kindly provide our office space and event support. This event is one of the ways we support the public sector in our region and wider by sharing knowledge, building connections, and really increasing understanding around low carbon technologies. Heat pumps are a big topic. We've broken it down into 5 sessions, and it's really to give you a clear understanding of how heat pumps operate. We covered a high-level overview last time on how heat pumps work. Today, Matt's going to lead us through planning and specification, and then we've got more sessions coming up, which I hope you all look forward to. We will send the registration links out to the next sessions ahead of them, so you can register for them. So please keep an eye out for them, and by all means share them with colleagues. I'll hand over to Matt. Matt Fitzpatrick has been with Stiebel Eltron for many years. Stiebel Eltron, 100-year-old company from Germany. They've spent 50 years working in this space. Heat pumps are not new technology. They're old technology, just maybe new to some of us. Without further ado, I think I will hand over to Matt, who is their specification engineer and lead trainer as well. So we're in good hands. Matt, over to you.
Thank you very much for the introduction. So in today's session, we're going to look at planning and specification. So there's a few key points to remember when you're planning or specifying an air source or ground source heat pump. We will cover understanding the heat loss of the property and a brief introduction to heat loss calculations. We will look at the benefits of inverter modulation. This is a critical technology which allows the heat pumps to be even more efficient. We will look at heat pump locations and site restrictions. We will touch on weather compensation and low flow temperatures. And on our final section, before our Q&A session at the end, at Stiebel Eltron, we have a free tool called the heat pump tool. It's used to help specify products for projects, either commercial or domestic. It's a really good insight into how to plan and specify a heat pump for a project, and also what is required. There are cost calculations, there are CO2 emission calculations, which are all integrated into this tool. And it's free of charge to use. There is no subscription fees, and it's really, really handy moving forwards. So initially, understanding heat losses. So heat is lost through the fabric of the property. This is normally the external walls, the roof, windows, doors, and floors. We will see some heat loss through internal rooms. For example, heat generated or provided to the ground floor will rise and go to the first floor and second floor, and so on. Normally, we will target 21 degrees in the living areas. So this is normally the first floor, the ground floor area. So kitchen, living room and dining room, and any office space on the ground floor. We then target, as a standard for the industry, 18 degrees on the first and second floor. So these will have a lower design temperature. And as I was saying, as the heat rises from the ground floor, it will start to heat up the second floor or the first floor. These will require less energy to heat these rooms. And this is normally accounted for in the heat loss calculations. So the standard design temperatures are 21 degrees for living areas and 18 degrees for bedrooms. There's always a question of, should I take the fabric first approach and insulate every aspect of the property? I've put a graph up on the slide, and this just shows that we don't always need to insulate every aspect of the property. Adding insulation will greatly reduce the heat loss of the property. This is going to be beneficial. However, even with partial insulation being added, for example, loft, upgrading windows and doors to UPVC double glazed or triple glazed windows and doors, external wall insulation, suspended floor insulation, all of these will start to reduce the heat loss through the fabric of the property, giving us a better control aspect. And what I mean by this, if we look at a typical existing property, we can see the heat loss is made up of 80% of the fabric loss of the property and 20% or around 25% through ventilation loss. This is drafts, this is windows that aren't fully flush to the wall and do have a small air gap or any air bricks. Anything that can cause cold external air to come into the property. What we can do is add insulation and we can reduce the fabric loss down to 60%. And then we have a more controlled heat loss of the property. We will still see ventilation loss, but this can then be controlled through mechanical ventilation heat recovery systems, or NVHR for short. The idea is, if we can start to add insulation and calculate the heat loss with the new proposed changes, we then have a more stable basis. We can understand exactly how much energy we will lose, and this allows it to specify the heat pump correctly to the property. When you start adding aspects of insulation to a property, we can then reduce the size of the heat pump that is required. So we could take a heat loss of a property that we'll say is 12 kilowatts with insulation to as low as 7 or 8 kilowatts, which means we've gone from a very large unit down to the average size unit in the UK. Most homes in the UK on average are between 7 and 10 kilowatts heat loss. If we add NVHR systems to a well-insulated property, we can then potentially save an additional 15% in heat loss, because we're recovering the heat inside the property by bringing fresh air in as well. So it's all beneficial. So as I've mentioned, heat pumps are designed to match the heat loss of the property at the design temperature. Now this varies across the UK. Scotland is -5, London is around 1 degrees. For our local area, it's around -3. So we need to design it to -3. We need to ensure that the output of the heat pump is correct for the property at that temperature. So we'll have a look at the benefits of inverter modulation. So inverter modulation allows the heat pump to increase and decrease its output. So it could be range rated from 1.5 kilowatts to 8 kilowatts, and it can deliver a maximum of 8 kilowatts and as little as 1.5. The reason you will see a benefit of using inverter modulation is because the heat loss of the property changes. At design temperature -3, it could have a heat loss of 8 kilowatts, but at 5 to 7 degrees, which is our average heating season temperature, it could be as little as 4. Now, it's inefficient to try and deliver 8 kilowatts to a property that only needs 4 kilowatts. So our inverter modulation then reduces the output of the heat pump to perfectly match the amount of energy the home requires. And we can see here the heat demand, so how many kilowatt hours we need to heat a home between the outside air temperature of 4 to 10 degrees on an average property in the CH62 postcode requires 6,627 kilowatt hours. Now our design temperature, so we've gone 6 degrees from design temperature, so -3 to 3 degrees, requires 2,585 kilowatt hours, so 3 times as less energy at the design temperature. So we really want to make it more efficient in that 6,627 kilowatt hour period. Now with the inverter modulation, especially in our products, we will use the outside air temperature and look at the internal temperatures in the property. And we can then program the control system, which is an adaptive control system, to generate enough energy to the property. But as you can imagine, if the homeowner comes in and they've left windows and doors open, that 4 kilowatt heat loss may now be 5. So the clever controls inside our heat pumps will read all of the data, analyze it, and then increase the output of the heat pump to 5 kilowatts to perfectly match the property demand. So heat pump locations and restrictions. Air source heat pumps require a large volume of air. Now, if we restrict the airflow rates or we reduce the extraction rate of the exhaust air, we can cause faults or poor performance. So during the heating season, we can still have cool days with high humidity, and this can cause the heat pump to build up frost on the evaporator as there's excess humidity, and we're taking the air temperature down to low 1 to 3 degree temperatures, even sub-zero in some cases, depending on the outside air temperature. So we need to ensure there's sufficient area around the heat pump. If we don't, we can start to see problems arise with the defrost operation or the defrost cycle, which allows the heat pump to thaw out of the evaporator and then continue operation. This is crucial because heat pumps can use up to 80 litres of water from the home or the buffer cylinder to complete a defrost cycle. And if the heat pump doesn't have the area it needs, it can start extracting 80 litres once or twice, potentially an hour, during those colder months, which then creates an inefficient heating system. So for our equipment, we need between 1 and 2 meters in front of the heat pump for our exhaust air. And cold air falls to the ground relatively quickly. It's quite dense. So we need the 1 to 2 meters to allow the airflow to move away from the heat pump and fall to the ground and not recirculate into that fresh, warmer air that we're trying to extract the energy from. Our brand new R290 refrigerant units, air source units, only need a 600 ml clearance in front of the fan area or in front of the fan, which is the same size as a kitchen worktop. So it really depends on the area you're looking to install the heat pump. They will also need a condensate drain. So it could either be a concrete plinth with a soakaway in the base, or it could be a gravel trap below. And that's to catch any additional condensate after defrost cycles. You also need to ensure a sufficient space for servicing and maintenance. So that's going to be either side and behind the unit. So if you do need to access it for servicing, maintenance, a general clean or removing leaves in autumn, you need the space there as well. With R290 refrigerants, which is the latest refrigerant on the market, there are safety exclusion zones, and these are critical. R290 refrigerant is a propane-based refrigerant, and you need to ensure that you have at least a meter clearance either side of the heat pump away from electrical sockets and electrical outlets, opening windows and doors, and drains. At the top of the unit, you require less space. For our products, it's only 10 centimeters, so any electrical connections can go above the heat pump. and we'll have a brief look at the internal system. So plant room integration is important. We don't always have a large technical room to be able to install all of the equipment. So what we can do is utilize various products, such as integrated units, as we can see in the image on the screen. This looks ever so slightly like an American fridge freezer. This contains circulation pumps, a domestic hot water cylinder, a buffer cylinder for the radiators and under the floor, and your main controls. And it fits in one perfect unit. And then, as we can see in this example, it's in a utility room. You'll also need to make sure there's sufficient space for any internal components to be able to service them and access them. Air source and ground source plant rooms differ slightly because the heat pump is then inside the plant room, so you will need a slightly larger plant room. But again, with most ground source applications, it's a slightly larger property that has the area or volume that we need for a plant room. So weather compensation and flow temperatures. I have two examples on the screen, and when we talk about weather compensation and flow temperatures, we always try and target the lowest possible flow temperature that we can achieve. And this is for efficiency. If we only need to provide a 35-degree flow temperature from the heat pump to heat a room to 21 or 22 degrees, we aren't wasting as much energy, so we're a lot more efficient. In this example, I've used a 6 kilowatt property, so a heat loss of 6 kilowatts, and I've set the flow temperature at 35 degrees. At 5 degrees for our 290 refrigerant units, at 50% capacity, we are achieving a COP, or coefficient of performance, of 5, which is 500% efficient. That means we only spend 24 pence for 1 kilowatt of energy, and we receive 4 free. And this is all to do with that low flow temperature. And as it gets colder outside, our flow temperature will increase ever so slightly, which I will show you in the live demonstration. Now, if we look at the exact same system, exact same heat pump and property, but this time I've set the flow temperature to 60 degrees. This is what you would see for a common combi boiler. And with 5 degrees, we are around 2.9% for a COP, so 290% efficient. We are 200% less efficient at 60 degrees. As it gets colder, you can see our efficiency starting to reduce. For a heat pump, the ideal efficiency is between 3.5 and 4. That makes it the same running cost as natural gas. Anything above that, we can start to be even cheaper than natural gas. So that's the end of our presentation. What I would like to do now is demonstrate our online tool. So this is our online heat pump tool. Sorry, let me just close this window. There we go. And very brief instruction how to use it and how we can use it to specify heat pumps for various properties. So the first tab on the top is the property type itself. So we will say it's a single family house. We have a standard level of insulation. We have a 7 kilowatt heat loss. And we'll just use a local postcode, CH62. With this information at the bottom, we're now collecting what we call degree day data, which is found in the MCS lookup chart to tell us our run hours for the heating season and the average temperatures. We can then select hot water, so domestic hot water. How will we be heating the hot water? We'll use our heat pump. Demand per person per day, which is normal, 25 litres at 60 degrees per person. We'll hold the cylinder temperature at 50 degrees. We're not using any additional domestic hot water circulation, and it's going to run for a full year, so it's not in partial use. Now what we can see here is the in the red shaded area is the output of the heat pump. This grey line is the heat loss of the property. So our design temperature at -3 is 7 kilowatts. Our heat pump can deliver 7.3, which is fantastic. It's always good to have some redundancy. I say when you're specifying a heat pump, try and have between 5 and 15%. So if your property needs 7 kilowatts and you have a unit that's 7.5 or 7.8, that is perfectly fine. If you had a property that is a 7 kilowatt heat loss and you add a 14 kilowatt unit, this is way oversized. It will cause the heat pump to cycle. So we can see as it gets warmer outside, for example, at 5 degrees, our property only needs 3.3 kilowatts. However, our heat pump can modulate down to as low as 2.6 or perfectly to 3.4, which will satisfy the property. And by doing this, we can then make the property and the heat pump a lot more efficient. We can run what I call low and slow. Low flow temperatures, longer running periods, better efficiency. And then this can be transferred into heat demand. So we will see on average at 5 degrees throughout the heating season, 1,338 kilowatt hours to heat the building and 91 kilowatt hours for hot water. So this now allows us to see where the worst case scenarios are, how much energy we need at different temperatures, and if there are other renewable products like solar PV, NWNZH, how they will integrate to the heat loss and building requirements at this stage. We can also see electricity consumption, which is quite interesting and very handy. So we will use the most amount of energy around 5 degrees, which equates to 237 kilowatt hours. Now that is across the full heating season, so September to March on average. And then costs. So we can use this to show the running cost differential between oil, gas, LPG. So if we say our electrical price is pence per kilowatt is 24 pence. Sorry, bear with me. There we go. Gas is around 8 pence per kilowatt, and we will leave oil at 11 pence per kilowatt. So the heat pump will cost £580 per year to run. And this is based on £423 per year for space heating and £157 per year for hot water. So very, very low running costs. We can look at the performance of the unit. So for example, at 9 degrees outside air temperature, the heat pump I've selected, which is our 7.2 kilowatt HPA R290 heat pump, has a COP of 5.46, so it's 546% efficient. And at colder temperatures, 5 degrees, it's has a COP of 4.92, so 492% efficient. We then have comparisons as well. So at this point, we're looking at energy costs. So we can see in current prices, a gas central heating system for this 7 kilowatt property in CH62 postcode would cost £1,127, and that's at 8 pence per kilowatt for gas. And at 24 pence per kilowatt for electric, the heat pump is £580 a year to run, so almost half the running costs of gas. As things change and prices change through various factors, if we predict the running costs in 9 years' time, it's £757 for the air source heat pump and £1,825 a year for that combi boiler system. So we can see, even over 10 years, the heat pump is still half cost, twice as less to run than a gas system. When it comes down to oil, that's quite interesting because oil heating systems can be expensive. And if we do a comparison between the air source heat pump and oil heating, it's £2,500 to heat a 7 kilowatt property by oil, but it's only £757 for an air source heat pump in year 2034, and its current year, it's 3 times cheaper to use an air source heat pump. You can also add this into a PDF. So if you are looking at information for a property, you can add that down, or you can leave it blank, and it will generate a 30 or so page PDF document with all of this information that we have here. I'm sure I will probably have some questions on the tool, or the heat pump tool. I think we are getting close to our Q&A session. So if I stop sharing the screen for a moment, should we jump into our Q&A session?
Thank you, Matt. No, that was good. And that tool, just to remind everybody, is freely available. The link Namita has put into chat. So that's a tool for people to go and play with. In terms of problems that you see in the field, Matt, what are the sort of typical symptoms of a bad install that you'd see? Because I'm sure many of us go and look at heat pump installs as part of demonstrations. What would be the typical signs that you see of bad installs? What should people be on the lookout for?
The top 5 I would normally mention would be high running costs. So if a customer reports high running costs, I would check that the radiator sizing is correct, and also the heat pump hasn't been left on what we call a fixed value operation, which could be 50, 55, 60 degrees. These will cause high running costs. The other scenario is the defrost. If a heat pump isn't installed with sufficient volume or area, or there isn't any system volume for the heat pump to be able to collect the energy from during a defrost cycle, it can cause a lot of problems and an inefficient system. You may also find, when specifying heat pumps, that the name or the label might say this model number 15 or 12 or 13. That doesn't always mean it's the kilowatt output. So you should always check in technical data provided by the manufacturer to ensure that at your design temperature, the heat pump can deliver the energy that you need. Because if not, that 15 kilowatts, or the product named 15, may only deliver 12 kilowatts at your design temperature when you need 13 or 14, which means it's insufficient and cannot heat the property. I think the other one as well normally is there's a huge debate in the industry of what we call buffer versus bufferless, which is having a volume of water to heat or to provide heat to radiators and underfloor. You should always ensure you've got sufficient volume if you are going bufferless, because you need energy for heating. If the heat pump's been off or on a reduced temperature overnight and the heating switches on, you may have a clash between domestic hot water priority operation and heating. So the heat pump will favour domestic hot water because it's a shorter cycle and it's in demand and use, and neglect heating for that period. So the property may go cold. So you should always make sure you've got sufficient volume in either buffer or bufferless designs.
Okay. And then I saw that clearly your example showed how much cheaper the heat pump was relative to electricity. But in reality, for the UK, we've got electricity prices of, say, 21, 22p a kilowatt, and gas is sitting at 4, 5, 6, 7p a kilowatt. that means we need COPs, do we not, of about 3.5 minimum, 4 minimum before we start break even? What's your views there?
So COPs of 3.5 are easily achievable. In my opinion, it's the baseline that you should achieve. I think even with MCS that you need to achieve a minimum COP of 3.5, but I will double check that figure. With the latest technology, inverter modulation, 3.5 or 4 is where, if it was one of our systems, I would start to investigate to see why the COP was only 3.5 or 4. With the values that we achieve in the field, I would start to investigate to see why that isn't performing as I'd expect. But it's very, very easy. Ground source, even air source, can quite easily achieve COPs of 4.5, 5, 5.5, especially with R290 refrigerants. That is easily achievable.
Okay. And then the other thing that really struck me was, the installation of an American fridge freezer, and that's fine for some properties, but many of our residents are living in, smaller houses. How do we go about fitting? We don't have anything like a plant room in a small house. How do we go about fitting a heat pump into smaller properties?
So smaller properties, they're no longer a challenge. We have pre-plumb cylinders, and they are quite common on the market, which are smaller capacity cylinders ranging between 200 to 250 or so litres, 225 in our example, with a buffer and a domestic hot water cylinder built in. And our pre-plumb cylinder is only 750 mil in diameter. So it will fit in an existing airing cupboard or hot water cylinder cupboard. And then the flow and returns from the heat pump, so the pipework from the outdoor unit, can normally come in through the property and then up to the cylinder cupboard. But they can be integrated into kitchen areas or underneath stairs. If there's loft space, it can go into loft spaces. There are different applications in or different products for each application, but smaller homes are no longer a problem.
Right. Okay. And just to iterate to the people on the call, if you do have additional questions, please just drop them straight into chat, and then I'll get them relayed over to Matt. Matt, in terms of installer base, and this is just looking at the wider industry, we've got lots of gas certified installers running around, and they're certified because you've got a gas certification process system in place. How do people know that their installer is good and that's been properly sized?
So the MCS, or any installer who is registered under the MCS scheme, will complete full heat loss calculations on the property, and then sign off, obviously, on what they've calculated. A heat loss calculation is quite extensive. I've ran through it in 5 or 10 minutes, but in reality, it can be 2-3 hours on site, depending on the size of the property. So most installers who are MCS accredited will do the heat loss calculations, and obviously MCS is a governing body. And always have a look at previous installations, what the installer has done. Most manufacturers are also happy to recommend installers in the area. For ourselves, we have a close relationship with our installers. We work with them quite closely. They come through multiple training sessions, and it's always ongoing. As a specification manager myself, I go to site with installers to discuss the project, help size the product. Sorry, not size the product. Size the cylinders, check for the area, and add some reassurance. So it's always working with the manufacturer and also the installer. So it's a triangle, effectively. The installer and the manufacturer work alongside your requirements, the customer or the end user.
Okay, and you should clearly be able to see that heat loss assessment for your building and be able to interrogate the installer as to the how they've gone about it. A couple of questions come through, Brian. This is for hot water storage. I think you mentioned earlier that you were storing hot water at 50 degrees. And Brian's question is that warm enough for Legionella prevention on a domestic tank?
So Legionella prevention for ourselves is once a week. So it will take place once a week, and it will increase the tank temperature to 60 degrees and then return it back to 50 degrees. The reason we don't store cylinders at 60 degrees at all times is it's incredibly inefficient. If you look at a kitchen sink, people will try and supply 60 degrees to the kitchen sink to wash dishes, cups, plates. But inevitably you add cold water in to blend it down to around 40, 45 degrees, which is bearable. So you don't want to waste the energy holding a tank at 60 degrees all of the time, when for that Legionella cycle, it only needs to happen once a week.
Okay. And just a quick note from Fiona, the heat pump tool that we've shared, apparently it requires a login. Is that correct, Namitha?
Yes, you will need to log in for it. There's no charge. But again, it's the only tool. There is another one which we do not require a login called the Navigator tool, which is just a basic form of the heat pump tool. So it does require a login, but it is free to use.
And is that a login that they can obtain? Is that just a free registration type thing?
Free registration, yes. So you would, on heat pump tool, you will have a profile button and you could just click register.
Okay. Right. Jamie, on that very first slide of yours, you showed that ventilation caused 25 to 35% of the heat loss. And if we used mechanical heat recovery from the ventilation, we could claw back 15%. And why can't we claw back the full 25 to 35%?
Okay, very, very good question. Simplest answer is how the building is constructed. If you take a 90, we'll say a solid brick wall 1920s property that was built in such a way to naturally have air passing through, has or had open chimneys, suspended voids underneath the floors and air bricks. If you seal those ventilation points off, you will cause damp and mold in the properties, and you cannot effectively get rid of it once it's all sealed. So there are points where you can take a retrofit property and insulate it to almost what we call retro passive house, but you will require NVHR at that point for humidity control as well. Now you can reduce that 25 to 30% by insulating the property, but with the fabric approach of putting partial insulation in and still having some ventilation loss, it's easier to control your fabric loss rather than ventilation loss. Because if you have a 10-meter wall that has a heat loss of 500 watts, but then has several air gaps in there allowing fresh air to come in, your heat loss may no longer be 500 watts for that wall. It could be a kilowatt, or it could be 1.2 kilowatts. However, this heat loss becomes a variation on the cold draft coming in. So if you reduce the heat loss of the fabric of the property, so those walls you insulate them when you stop that draft coming in, you have a better control of the heat loss, only allowing for controlled ventilation, so through trickle vents or extraction fans. You will always still need some ventilation, but it depends on the age of the property.
Yeah, I think we should also point out that your chart showed to 100% in all cases. They didn't actually show that on a clearly uninsulated property, your absolute heat loss was significantly higher than an insulated property. Yes. So the chart was a little
off. Sorry,
a little off. Fiona here. If we're going to put cylinders up in the loft, and got a requirement up in the loft for say 300 mil of insulation, is the loft, do we need to reinforce that loft? Do we need platforms to land above the insulation? what's the impact of having the tank above the insulation as well? You're now in a cold zone. Do you want to just expand on that?
Okay, so you should never compact loft insulation. So that always needs to be kept at its distance with sufficient airflow. There are options to strengthen the areas. When it comes down to installing cylinders in the loft, it can be done, but I would say on a list, it's right at the bottom. I wouldn't use it as a priority option. I would try and keep the cylinder on a first or second floor, or ground or first floor, I should say, for ease of access. You don't really want a service and maintenance engineer having to go into the loft once a year to complete G3 servicing on a cylinder. It can be strengthened. There are horizontal cylinders on the market as well, which are a lot easier. They spread the load, and it depends on the size of the capacity. If it's a small property that needs 200 litres, then our stainless steel cylinder weighs 70 or so kilograms dry, which is pretty light in the way of cylinders, and wouldn't need as much strengthening. But if you're trying to install a 400, 500, 600 litre cylinder in a loft, apart from the difficulties trying to get it in there, you would need severe support. So I would try and say if it's a small cylinder, yes, but it's the worst case option, worst of the best case scenario to install into the loft.
And I imagine getting that size vessel into the loft probably means going in through the roof rather than through a narrow loft hatch.
Correct. Yes.
Right. Okay. The build out of skills, installer skills on the installer base across the Northwest. Clearly, and I should have clarified this for everybody watching. We're not endorsing Stiebel Eltron in any way. They're very kindly providing this because they've got a technical centre near our office here in Liverpool. But are you supporting not only the installation of your equipment, but what's the picture of independent installers? What's the overall landscape of the installer skills base in the area, and how do you as a supplier fit into that sort of ecosystem?
So for ourselves, we work closely with local colleges and universities to provide support and education on how to specify heat pumps, how to integrate it into their existing modules for heating and plumbing. We will train local installers and, well, to be fair, national installers on our equipment. As you can imagine, myself from Stiebel Eltron couldn't train an installer on a different manufacturer's product because my knowledge on that product specifically wouldn't be as good as the manufacturer. But there are BTEC courses and various courses on renewables throughout the UK. They are starting to become more and more common, and we are finding that colleges and universities and educational facilities are implementing these into their normal standardized curriculum. I do know of a few colleges that we have nationally where we support them quite well with products and open days, and I think it's progressing at a steady pace.
Mm-hmm. And is it the case, as with gas engineers, that if you're gas certified, what gas boiler you put in, you're fairly agnostic. You'll have a preference based on experience, but you can install pretty much anything. If you're trained in heat pump installation, does that allow you to switch between manufacturers, or are you tied in?
No, if you have completed the accreditations to be a renewable installer, you could choose any manufacturer. You don't have to stay to one brand. Each manufacturer has a different or slightly different way of installing the product and specifying systems or different product range. So the only educational process for the installer would be manufacturer A has products that provide 7, 8, and 12 kilowatts, whereas manufacturer B has 9, 11, and 13, for example. So it's only the product knowledge, but that's when manufacturers come in and guide the installer through their product range and system design, so they will have an unbiased view of all the products and a good knowledge of manufacturers out there as well.
Yeah. So a little query on safety, and I'll come on to a couple of questions from Brian. Do we need to restrict access by children and pets? Do we need a cage around the unit, or does that restrict cycling? But I've got the question, but yeah, let's see.
Okay, so normally they are quite secure, and the electrical connections are closed and screwed shut. It's very difficult for children, even adults, to put the finger into the fan, especially with ourselves. We try and recess the fan a fair distance away from the grill to ensure that if a child does try and squeeze the finger through, it's not going to come in contact. In regards to the cage, you can put protective covers around the heat pumps, but they need to allow airflow. So a cage is a fantastic example. If you had a cage built around the heat pump with ample aspects of airflow to get through the cage, not a problem. If you had like a wheelie bin shed is the best way to describe it, a bin shed, and the front had a slatted open fence panel, that again is okay, because we're allowing the air to transfer from the back of the air source heat pump and out to the fan at the front.
Yeah. We've spoken a lot about the need for buffer storage and the size of the water tanks and sort of the sort of thermal inertia within the system that you can maintain. What are your views on phase change material storage? Certainly, and this would relate certainly back to smaller properties that don't have the space. Phase change material, we haven't really touched on that in this. Do you want to just explain a little bit more about PCM?
So phase change material is a product that can supply high temperatures. It's a difficult one to describe. Probably the best way to describe it, we've all seen the hand warmers in winter, where you can squeeze them, create some kind of mechanical input, and then the agent inside activate and then provide warmth. A phase change material in the renewable industry is pretty much very similar. We can supply the energy from an air source heat pump at a high flow temperature to the phase change material, which then stores the energy and can be used to heat up domestic hot water. We have had products tested with phase change material manufacturers currently on the market with great success. It is a solution for small spaces. I think probably 5% of the market would utilize phase change material if space is a restriction. We can normally fit tanks and cylinders and the equipment we need into properties without losing dramatic or large areas of space. But it has been used before. We've done quite a lot of testing with it, and it was quite successful.
Okay. And then a technical one on installation is handling the refrigerants. Does that need special qualifications, preloaded? And what are the environmental risks of some of the refrigerants you've mentioned?
Okay, so you will need what we call an F-gas, which is a refrigerant qualification, if you are actively servicing the refrigeration circuit. Now, we only supply monoblock heat pumps. Monoblock means the refrigeration circuit is inside the heat pump. It's completely closed, a bit like a fridge freezer, really. At the back of the fridge freezer, at the bottom, is your refrigerant circuit, and our heat pump is the same. We have a sealed refrigerant circuit. If you ever need to service that refrigerant circuit, you would then need an F-gas qualification. You do not need an F-gas qualification to install monoblock heat pumps, just plumbing and electrical qualifications to be a competent plumber and electrician. And the aspect of refrigerants is there are certain refrigerants which do a greater damage to the ozone layer, and we will categorize them through GWP or global warming potential. Some refrigerants have a very, very high GWP, and we're targeted to have products which have the lowest GWP. So, for example, R410A has a GWP of, I think it's either 3 or 5, which is exceptionally low, which means it's now future-proofed for many, many years to come, because the damage or potential damage it can cause to the ozone layer is minimal compared to a refrigerant from 10 or 15 years ago, for example, like R134A. That has a very, very high GWP. We are seeing refrigerants being phased out because of their GWP. R32, which is a common refrigerant, is one of those refrigerants being phased out, which again adds the complication of, if you can't gain the clearances for an R290 unit, you will have to look for another solution, which is why we offer R454C refrigerant heat pumps, which don't need safety exclusion zones, but still have a very low GWP, global warming potential.
Okay. Yeah, so I mean, we should be saying that that's all relative to carbon dioxide.
Yes.
In terms of that ratio. So I'm just looking at the time. We've got time for a few more questions. We're looking there at well, probably efficiency. So below 2 degrees. Comment here from Chris, who's had COPs drop below 2 degrees to the extent that they can't then heat the required heat the house. And then one of the other challenges is, we've got different heat pump tariffs. So describe the working of the heat pump when it actually, because we've got to notify the energy provider that we're installing a heat pump, and we're placing additional load on the house, and I assume that load is going to come on and come off. Is there a way of linking when it comes on to when we have cheap power? What are the controls available there? So 2 questions really. How do we stay efficient, and how do we use cheap power?
Okay, look, I will go for the efficiency first and then come back to the controls. So yes, the below minus 2 degree problem that you've seen with underperformance, underachieving, is down to the output of the heat pump. So there will be a technical graph that shows as the outside air temperature drops, as does the output of the heat pump. So for this one, you should always contact the manufacturer. We try and give as much information as possible because you don't want to install a heat pump that underperforms. The other thing to bear in mind as well is the 5 kilowatt unit. Then you have to ask the question about domestic hot water, because if that 5 kilowatt unit only provides 3 kilowatt output at -2, and you're trying to reheat a 250 litre domestic hot water cylinder, you've only got 3 kilowatts of energy to do so, and it will take quite a long time to achieve that set temperature. And during all the while it's trying to heat domestic hot water, the home is being starved of heating. And as the heat pump switches back over to satisfy heating, and it can only provide 3 kilowatts because that's all the unit can do at that temperature, your heat loss is 5 kilowatts. So you're already 2 kilowatts above what the unit can provide, plus the cool down time after that domestic hot water cycle. So this is where I mentioned there's no harm in slightly oversizing the heat pump. So if, for example, you had a property that had a 5 kilowatt heat loss, I would specify a 7.5 kilowatts, because we can modulate down to match the property demand, but we still have that quick recovery time for domestic hot water. And the energy tariffs,
before we jump into tariffs, does that mean the property owner has a choice? You either need to put a larger heat pump in, or you need to look at the fabric of your building and reduce the heat demand so that you're actually matching what the heat pump you've got. And I guess there's swings and roundabouts on costs there.
There is. So if you reduce the heat loss significantly, you can then cause a heat pump to cycle because its minimum output might be 2 kilowatts or 1 kilowatt at design temperature. But during the higher average temperatures through the heating season, the heat pump delivers far too much energy than the property needs. So the heat pump is on and off, on and off. So in this scenario, you've got to look at hot water and the property, and also the technology inside the heat pump. If the heat pump can perfectly match the property demand through inverter modulation and clever control systems, then you don't need to worry too much about that 5 kilowatts heat loss because the controls will provide exactly what's required. It's the domestic hot water cycle on average. The heat output, a property needs 10% of its overall energy for domestic hot water, 90% is for heating. So if we start increasing it, then increasing hot water, we will start the heating system effectively.
I'm aware we're tight on time. Do you want to dive straight into that cost tariff issue? Because I think that's going to be of great interest.
Okay, so there are heat pump specific tariffs out there. You need to be careful with the running of a heat pump because you can't run them like a gas boiler. So you have to have a heat pump running in a lower setback temperature. For example, when there is no activity or requirement in the property overnight or when someone's at work between 9 and 5. If you try and have a heat pump switching on and off at cheaper rates and provide all of the energy, you will need to oversize the heat pump incredibly, large oversizing to catch up with the heat loss of the property, increase the flow temperatures, and inevitably decrease the efficiency. If it's done where you can use those cheaper tariffs to preload a buffer cylinder with a higher temperature and have a better efficiency, or preload a domestic hot water cylinder to 60 degrees, 65, for example, and then allow the heat pump to remain off for longer, that will be the bigger benefit rather than trying to cycle them on and off.
Okay, well, thank you very much for that. We're coming up to the top of the hour. We have, as I said, this is part of an ongoing series on heat pumps. So, Rihanna, it's a great question, but I'm afraid we're going to leave that for a later one. The links and the emails will go out for the next session. This session is being recorded, and we'll load that up onto our website. And we're top of the hour. I'd like to say thank you to Matt. Thank you to Matt, Namith, for putting this together. Have a nice day.